Swayam Prabha. Digital India. Educated India.
Let us resume our discussion on the Joule-Thompson experiment, and I have talked about it, but the point that we need to note is the following: that is an adiabatic irreversible expansion of a gas, and in this case what is happening, that you have a higher pressure on the left hand side and lower pressure on the right hand side, and there is a fall of pressure, and because of this fall of pressure you observe the drop in temperature. So that has a very interesting consequences. And to analyze this particular case, we first note that this is an adiabatic experiment is carried out under adiabatic condition. So adiabatic condition tells us D, that is Q is equal to 0. That is, no heat has entered or come out of the system, and you have purely we have to work only with internal energy and work. So delta E plus W, that is equal to 0, because Q is equal to 0. So now the point is that I need to calculate this W, and for this process, so work W can be carried out in this can be worked out as follows: that W is basically the work that has been. So what is being done here, when I am pushing it from left to right, so on the left hand side, so on the left hand side, what is going on, I push the gas from the left hand side from the volume V1 to 0. So I go from here V1 to 0 against a pressure P1. So it is P1 times dV. So that's the work for the on the left hand side, and so W left and W right on the right hand side. What is going on? You have from 0. So if your piston is close to almost touches this diaphragm, then it is volume is 0. So W right is basically you are going to expand from 0 to V2, 0 to V2, and against P2 dV. So this gives me P1 minus P1 V1, and here it is P2 times V2. So total work W is basically P2 V2 minus P1 V1. So now delta E, so we have from this delta E is basically delta E is equal to E2 minus E1, the change in internal energy for the two states, and so you have E2 minus E1 plus W P2 V2 minus P1 V1, that is equal to 0. So it means you have E2 plus P2 V2 minus U1 plus P1 V1 equal to 0. So this gives me that this is my enthalpy. So it is H2 minus H1, that gives me the change in enthalpy delta H, and that is equal to 0. That's an interesting thing. So in this adiabatic irreversible expansion that we have been discussing, we have a situation, there is a pressure drop and a correspondingly temperature drop, but the enthalpy does not change. So it is an isoenthalpic process. So this adiabatic irreversible expansion of this gas, so it is an Joule-Thompson effect. So Joule-Thompson effect is or Joule-Thompson process is an isoenthalpic process. That is an interesting thing, because in the process enthalpy does not change. That means dH equal to 0. Now if we look at it, look at the system, that now what are the consequences of this, what are the basic consequences of these things, that what is the relation between the pressure drop and the temperature drop? That is an important question. Now the pressure drop and the important pressure drop delta P has to be related to the temperature drop in some way, and that is the basic observation that I can see. And to understand this, we come back to the original equation, that TH, H is a function of temperature and pressure. So H is basically, that is del H del T at constant pressure times dt plus del H del P at constant temperature times dP. So that is the basic starting point of our discussion, and we try to find out this thing. So I see that this is equal to dH equal for an isoenthalpic process, for an isoenthalpic process, dH is equal to 0. That's very interesting. If dH is 0, then we can see how delta T, dt and dP can be related. Because I see that because of the fall in pressure, because a change in pressure creates a change in temperature. So this is a clue for understanding this these consequences. So if the left hand side is 0, that means del H del P, so that this quantity del H del P is basically del H del T at constant pressure is basically Cp, that we have already discussed. So it is Cp times dt, Cp times dt plus del H del P at constant temperature dP, it is equal to 0. Now you can see, for finite process, for a finite process, I can write Cp delta T equal to minus del H del P times delta P. Now I can write a delta T delta P is a quantity, and this quantity is coming up here because of this isoenthalpic condition. So I put here H equal to, at constant H, that has to be carried out. So this equal to it is minus 1 by Cp times del H del P at constant temperature. So I can see that this is an interesting quantity, because that relates that if I make a drop in pressure, I observe a drop in temperature. So this is basically a kind of coefficient, and and more appropriately, if I can put a minus sign here, I can put a minus sign here to make it to give you a feel that there is a drop in pressure. So that del P and del T, this is a coefficient. We call it the Joule-Thomson coefficient. So Joule-Thomson coefficient mu J_T Joule-Thomson equal to delta T delta P at constant H. If I write it, then I can see that mu J_T is an interesting coefficient that can be related to minus 1 by Cp times del H del P at constant temperature. Or we wanted to learn more about this del H del P. So more about del H del P means that this is a quantity which is related to two important properties, that is, one is the Cp. So that gives me that del H del P at constant temperature is equal to minus Cp So you can relate this experiment also in the relate this coefficient also in this way. So it is basically basically a relation between certain properties. So Cp is a property of the gas. Joule-Thomson coefficient is a property of the gas. It depends on the nature of the gas, and del P del T. And this, if you multiply these quantities, you are going to get this del H del P. So del H del P is another property of the system. So this is a relation between the properties, and this relation is particularly important for many for technological point of view. This is because that when we see a drop in pressure, and if the drop in pressure is huge, if the drop is very large, the drop in pressure is very large, the drop in temperature can be very large also. So it means that if you release a gas from very high pressure to low pressure under some adiabatic condition, so that creates drop in temperature, and that drop in temperature may create certain observable things. First of all, and typical example is this, that if you have a container of nitrogen, that is a highly compressed nitrogen, and if you try to open partially the valve of it, then it immediately gets cooled, and cool the adjoining region in such a way that you see the drop snowflakes just around this valve. So that means the temperature drops severely from room temperature to below freezing temperature. So that is called the Joule-Thomson cooling. So creation of a drop in pressure drop pressure creates a in temperature. So that means this makes mu Jt positive. That means if you have a drop in temperature and correspondingly if you have a drop in pressure, then mu is always in that case is greater than 0. So in general, for all gases except hydrogen and helium, you have positive Joule-Thomson coefficient. For all gases except hydrogen, helium, except hydrogen and helium, mu Jt is positive. So actual calculation of this Joule-Thomson effect can be done by knowing this quantity del H del P from a different angle. Once we go over to second law and its consequences, from there onwards, and we will try to find out the actual expressions from del H del P from the other side and that will give us a more complete expression about this Joule-Thomson coefficient, and we will find out what is the condition under which Joule-Thomson coefficient is positive and when it is negative. So that condition can be obtained thermodynamically once we go over to second law, and that is for that we will wait for some time and move forward. And so this is basically the consequences of first and second law thermodynamics, and the main point is to stress that we have worked out several relations like this, which are the relation between the properties of the system. So one of the prime aims of thermodynamics is to discover the relation between the properties. So one aims of thermodynamics is to find out the relation between properties of substances. So that's a major aim. So this is a typical example where we see that this is a property. This property is related to Cp and Joule-Thomson coefficient in this way. So there may be other relations which are the consequences of this first law. So we'll try to move forward to discuss some of these relations, and they are actually important for many purposes and they have practical uses. And you know that this particular Joule-Thomson coefficient is very important for the technology of all refrigeration, because once you have when you release the gas from high pressure to low pressure, there is a drop in temperature, and if you recycle the gas again and again, and you see there will be continuous drop in temperature, and you can cool it as low as you like, above 0 temperature Kelvin. So that is a process, and so of course it has strong technological implications that you already know, and because of the various usages, and so we'll not discuss about it, but the main point behind it is this, that there is a coefficient which tells us which should be the which is a measure of the drop in temperature as a function of the pressure release. So that is a point that has to be calculated. One can calculate these quantities for various gases and make a table and so on. So we begin with certain properties of relation between properties, and few relations which are important and which are the consequences of the first law. So we come back to an important relation between the Cp and Cv. So relation So we come back to first law of thermodynamics. So it means that you have dq amount of heat that enters into the system, and that creates work dW and a change in internal energy of the system del E, and that is EW. And then I can write more explicitly dE plus P opposing pressure times dV for this mechanical work. So P opposing pressure is the pressure against which the gas moves, or the system gives the pressure. So this is a mechanical work done by the system. Now we know that what is this dE is basically if you write it as del E del V del T at constant volume times dt plus del E del V at constant temperature times dV. So dE is composed of these two terms plus P opposing times dV, and so this is dQ. So if I carry out this experiment at Cp, that is a constant pressure, so dQ at constant pressure dQp is equal to this quantity del E del V is basically the Cv times dt plus del E del V at constant temperature times dV plus P opposing dV. So if I write this, if I take we differentiate both sides with respect to temperature, you have dQ dt P constant pressure, that is equal to Cv plus del E del V at constant temperature plus P opposing dV at constant pressure. So this is basically, by definition, is Cp. So Cp is Cv plus del E del V at constant temperature plus P opposing times del V del T, and we have done this at constant pressure. So there will be a constant pressure So this is a Cp minus Cv is a quantity like this. So Cp minus Cv can be written down generally as del E del V at constant temperature plus P opposing times del V del T. So this is basically a relation, but if it is a property relation between the properties, that means Cp minus Cv, then this P opposing pressure means that the which balances this, it is basically the pressure, opposing pressure against work is being done by the system. So P, if P opposing, if it is, they are equilibrium properties. So Cp, Cv are equilibrium properties. Cp, Cv are equilibrium properties. Therefore, P opposing must be equal to the pressure of the internal pressure. So Cp minus Cv equal to del E del V at constant temperature plus P. Now you can write it as the P and del V del T at constant pressure. Now this is the most general relation for all substance. This is a general relation. This is a general relation for anything in this world. But you can interpret this quantity for, or you work out this quantity for specific cases. Say for example, an ideal gas is a standard case. For ideal gas, application to ideal gas, you have this PV equal to Watt T for 1 mole and pressure and del E del V at constant temperature equal to 0 because of Joule's experiment. This becomes more simpler than Cp minus Cv equal to 0 plus P. So it is basically P times del V del T at constant pressure. So del V del T at constant pressure means it is basically, if you differentiate this V with respect to T, then you have only R by P. You have P times R by P, so it gives you R. So Cp minus Cv equal to R is the celebrated relation, but note that there are certain tricky things which are not always mentioned but naturally included. But in the process of derivation, I have used this P opposing pressure because the work is, know how to introduce this work. It's a mechanical work. Always we write P opposing times dV, but since Cp minus Cv is basically the equilibrium properties, then I stated that the equilibrium condition can be maintained only your internal pressure is equal to the opposing pressure. Otherwise, there will be an instability in the system. So that creates your sets your P to be P opposing equal to P, and that gives me this particular condition. We will work out other relations in my next lecture. So with this, we thank you all.